will work. Okay, so now remember with the public key cryptography, we looked at the basic concept that you encrypt using somebody's public key, you send it to them, and they use their own private key to decrypt it. We looked at the advantages of it. We looked at the disadvantages of it. Then just to see, and it's useful in doing the project today, just to see the complexity of, or lack of complexity of math involved, I actually showed you the RSA algorithms, mathematics, which was basically a creation of the public key and the private key. And then encryption was basically raising the X to the power of the public key, and the decryption was raising Y to the power of the private key, modulo N. So you know all of that. Now that we know the theory of it, let's turn our attention through, again, step-by-step tutorial, and I add some stuff as we go on for today so that you would get a better feel for it. So we're going to be using the OpenSSL library to perform public key cryptography. Okay, so first thing, and again, I'm going to go through the help file, but every now and then I'll may switch things a little bit. So first thing we want to do, we want to generate the key. So remember, I said find two prime numbers, and then n would be p times q, and then phi of n would be p minus 1 times q minus 1. Again, it was good for us to see it, understand it, but on day-to-day basis, we don't expect people to start doing these silly things. So all of that key generation is written into a program which is part of the OpenSSL library, right? So you say OpenSSL gen RSA. So the name of the particular subprogram within this library is called gen RSA, generate RSA, okay? I put the option minus out, so by now you're familiar what that means. It means that what would follow it is the name of the output file that I would like the key to be stored in. So you can call it whatever you want, but I'm going to call it key.pem, and you'll see why in a second. And I put the number 1024. So I'm specifying actually the length of the, in bits, of the key to be generated by the program, right? So I'm saying OpenSSL generate RSA keys for me, put it in the file key.pem, and the length of the key would be 1024. So notice it didn't take long. So it found two large prime numbers, and then it did the steps that we looked at yesterday. So it says generating RSA private key, 1024-bit long modulus, and then E, remember, E is 65,537, or in hexadecimal 10001. Okay, so now what is of interest to you to know is that both the public key and the private key are in this file. So if you look at the file that was created, key.pem, both are in here. Now you may wonder, what does the extension P stand for? What would PEM stand for? Why did I even bother putting it? Remember, the extension doesn't mean anything, but why did I give it the extension PEM as opposed to something else? So PEM actually stands for Privacy Enhanced Email, which is the format, and it's in your tutorial, so you don't have to worry about it. But that is the format that the OpenSSL stores the public key and the private key in. Okay, so let's explore it. So the next obvious thing that comes to your mind is to say, let me look at the contents of key.pem file. Okay, so you look at it, so you do notice that it's not anything readable that would inform you of what the contents are. So the first thing comes to your mind is that, okay, it must be, contents should be binary, right? But it's not stored in raw binary, right? Because you notice you don't see those funny characters. It's all genuine alphanumeric characters. So what format do you suspect this is encoded in? Friendly looking binary, what was that? Base 64. right? So this is binary because it doesn't tell you much, right? But it's not those funny characters. So basically, you know, the ones and zeros are encoded into base 64, so it looks like a text file. But it's unreadable. There's nothing, you know, you can't say, oh, this is the public key, this is the private key. You can't tell anything in here, right? So, okay, so that's fine. But there is a utility, there's another utility within OpenSSL that opens up this file and breaks it up into its pieces and shows the results to you, right? So basically you're saying OpenSSL, analyze this file and show me what's in there, okay? So let's do that together. I'm going to say OpenSSL RSA, now not generate RSA anymore, RSA, okay? Dash in, which means that I want to specify what file I would like to be analyzed, which obviously was key.pem, okay? I'm telling it that the contents are in text format, and no out means do not display the contents in base 64, show them in hex format, okay? So the dash no out is not a big deal. You would have figured it out. It's nothing functional. We just want to see the results in hex format. So OpenSSL RSA, give me analysis of the key file, and you know, show me the results in hexadecimal. So now, having gone through the discussion at the end of the lecture yesterday, this makes a lot more sense to you. Not that you already need to know all the details of it, but at least you see what the program actually did. So take a look at it. It says private key. Modulus is 1024 bits. Remember, I said these are long numbers, not 3 and 11 that I looked at. These are long numbers. So this is the modulus. The public exponent is, you know, in hex this is, or in decimal 65,537. The private exponent, so the public and the private, right? It's this, okay? The first prime number, P, is this one. The second prime number, Q, is this guy, right? Exponent 1, exponent 2, and coefficient. And, you know, there's like a few other numbers that are used for optimization of the algorithm, right? But at least in general, and you could look at the documentation for this and see exactly what every element means. That wasn't my goal. My goal was that you see what is stored in that key.pem file is actually the public key and the private key combined. Because, okay, so this is good. But wait a second, I don't want my public key and private key to be in the same file. Remember, public key, I want to make it public. Private key, I want to keep it secure somewhere. So I should be able to extract the public key and the private key from this combined file. Okay, so that's the next thing. We're going to do. So I'm going to extract the public key, okay? So clear. So I'm going to say OpenSSL RSA, okay, so far, because I've generated the key, so I'm just playing around with the key, right? Dash in key.pem, so obviously I'm doing something, right? I'm saying run the RSA utility on the combined key file that I just created, but now I'm giving it an option. Dash pub out, meaning what? Extract the public port and take it out, okay? And obviously I have to give it a name, so minus out, and what would make sense, I'm gonna call it pubkey.pem. All right, so notice there's no mystery in here, right? So I'm calling the RSA utility. I'm saying the input to you is the combined public-private key file. I'm asking you to extract the public port out, pub out, and put it in this file. with whatever name I gave it, right? Now, of course, not everybody's file should be called popkey.pem. In my case, it would be like my name, popkey.name or .pem. All right, so it says writing RSA key. So if I look at the listing now, so you notice my public key is now extracted in this file, okay? I haven't done this, but let's try it. If it doesn't work, it doesn't work. I want to try to analyze this file. So remember, I analyzed the common file. So now I'm saying analyze this and show it to me. Okay. So yeah, no, so that analysis option works only on the combined file. So okay, it didn't work. Notice it's looking for the private key, it can't find it, it gets confused and gives me an error. All right, so now the question is that, and it's not in your tutorial, but we could do that. Right now, I have the combined file and I have the public file. What happens if I wanted to have the private file separate also, okay? From what I remember, and don't do it until I'll verify, if I use that extract command as before, right, OpenSSL RSA input is the combined file. If I don't put dash pop out, the option that output should be the public one, the output will be the private one. Let me just double check that quickly. I think that is indeed the case, but I had some additional notes in here. So I don't want to do encrypt yet. Okay, so I think so. So let's double check that in a minute. So, okay, so now take a look here. So I have it, it didn't give me an error, which means that, and I'm going to do what? I'm going to do a diff between private key and public key files. They should be different, right? So I'm going to say diff private key and pub key. Yeah, they're definitely different. So notice if I gave the option dash pub out, it extracts the public part. If I don't give it that option, it extracts the private key, right? So now, so as far as key generation, I'm done, okay? I do have my public key that I could make public, send to people, put on my website and whatnot. I have my private key that I want to keep secure. Okay, I don't want to keep it like this, by the way, on my hard disk, because I mentioned if somebody comes, they can copy it into a USB stick and walk away with it. So it would be nice if I stored it securely on my hard disk. Okay, so let's do this. So I'm going to say, I'm going to say clear. And it's in your tutorial. I'm going to say OpenSSL RSA. So it's in the RSA utilities. Input private key.pem dash des3 dash out private key. Let's say .encrypted, some silly name like that, all right? So what am I doing? I'm using the encryption tool within the RSA. By the way, notice I'm using DES. There's nothing wrong by just taking this file and feeding it to the triple DES as we did yesterday, okay? But it's built into the public key utilities as well. But notice I'm not doing public key cryptography right now. I'm actually taking this binary file and I'm encrypting it using triple DES, okay? So I'm saying RSA, take this file, the private key file and encrypt it using triple DES, which is a good one, right? It's secure, and put it in this file. Okay, and if I press enter, it says give me a password. Okay, so obviously you give it a secure password. I'm going to give it just a silly password like test right now. Okay, and test. All right, so now the good practice should be for me to go and delete this file. I don't want it plainly to sit on my hard disk, right? So what is sitting on my hard disk is this file. Anytime I need it, I would decrypt it, use it, and delete the decrypted version, right? So create some sort of a script to do this, okay? So everybody's following me, right? So right now, I'm not gonna use the file that I've highlighted, but I just wanted to show you good practice. You know, you don't keep your private key just sitting on in a folder, in a directory in your machine. You encrypt it and you delete the original version. All right, so we have all our keys set up, public keys out there, private key is securely stored. So what is the next thing? I would like to encrypt a file, a text file. So let's see, is there anything important in here? No, this is fine, we did that. So again, I need some sort of a text file, plain text, that I would like to encrypt. So I'm going to say nano plain text dot text. Now, as you will see, and I would look at it in a second, this RSA utility for public key cryptography is a very primitive function. It expects a block that is less than, what is the size? I forgot it somewhere. It's a small size file. Okay, maybe it is in my, no, it's not in here. So don't put a lot of text in there. So the idea being is that this utility encrypts a small amount of plain text. If you want to encrypt a large amount of plain text, you have to actually write some script or code to make multiple blocks and add them together. So, well, why didn't they do it, the nice way anyway? Remember, we're not going to use this to encrypt a lot of data. We use it to encrypt just basically the symmetric key of like a DES, triple DES, or whatnot. Okay, so I'm going to just put a couple of lines in here. I say here is my plain text, and the last line, just so that we have a couple of lines. So Control X, yes, press enter. So now I have my plain text. If I say cat plain text, okay, my plain text is there. So the next thing I need to do is to, okay, now we're doing it just mechanical work in here, but don't lose track of the meaning of what we're going to do now. I'm going to now encrypt this file. But remember, in this storytelling we're doing, the public key I'm going to use is not my public key. It's your public key, right? Because I'm encrypting it to send it to you, for you to decrypt it, right? So I'm not going to use my own public key. I'm going to use your public key. So remember, the public key I created right now, let's just pretend that it is yours. It's not mine, okay? So I'm going to say OpenSSL RSA util. So it looks like a weird word, RSA-UTL, RSA-util, so RSA utilities, okay? So the encrypt and decrypt are built into this program called RSA utilities. All right, so the next line, the next option is self-explanatory, right? I want to encrypt, okay? What file do I want to encrypt? Plain text.text. What does the next option say? It says, I'm specifying the file that contains the key, okay? And what key would I use? Public, right? So popkey.pem, right? And then I have to tell it that I'm giving you the public key, okay? Because remember, if I was doing digital signature, which we're gonna do after this, at the end of this project, I will be encrypting using the private key. So I have to tell it what I'm giving you because the format is different, right? So I'm telling it, I'm giving you, this is the key file, but it is the public key. Treat it as the public key because you remember, public key was the E and the N, the private key was the D and the phi event. So you have to remember, the program has to know what it's being given. So, and finally, the name of the output encrypted file, right? So minus out, and let's call it public key encrypted dot encrypted. You can come up with a better name, doesn't matter. So, all right. So I'm going to press enter. As soon as I press enter, it should take my plain text file, encrypted using the public key of the recipient, and give me the output file. Notice it went very quick. Okay. So ls. So now I have PK encrypted dot encrypted. Okay. Let's just, out of curiosity, look what's in there. So cat PK encrypted dot encrypted, and this is truly a binary file because I see garbage in there. Of course, I can use the XXD utility just to see inside. It's going to be a bunch of ones and zeros, but let's do that just out of curiosity. We don't have to do this. So XXD minus B binary PK enc. All right. So this is the public key encrypted version of that plain text file. All right. Which of course would have been the symmetric key for a triple DES or for an AES or whatever. Now I can send this file over the internet, not worried about anything. Why? Because supposedly the only person who can decrypt this file is the person who has the private key that pairs with this public key. So I'm sending it to destination. Now I'm the destination. Let's pretend now I'm the destination. I received this file. I have my own private key that the public key of it was used to encrypt this file, and now I'm going to decrypt it. Okay, nothing confusing. Okay, so let's do this. So I'm going to say OpenSSL RSA util, but this time I want to decrypt, right? Now, so you know that you already can tell the developers, the programmers that wrote the RSA utilities are different people from the developers that wrote the symmetric key cryptography code. Why? Because notice the convention used with the symmetric key programs was silly, okay? It was always encrypt, and then you put minus D meaning for decrypt. No minus D means it's encrypt, remember? These people who wrote this part of the library, were a little bit more logical in their approach. They said, all right, we're going to have an option decrypt and an option encrypt. That would be easy to understand, okay? But you could tell from the difference in style that obviously these are different people who wrote the code, right? So I'm doing RSA utilities decrypt. The file that I'm planning to decrypt is that PK enc.enc, right? Everybody agrees, the encrypted file that I received. I have to feed it the key. So dash in key is private key dot pem, right? And then let's see how it works. I'm doing it a little bit different. In the tutorial, the combined key file was fed to it. So we're going to probably run into trouble, but let's just go one step at a time. And I'm going to say minus out, let's say pk decrypt dot text. All right. All right. So it did the decryption. It did not complain. Okay. So first of all, let's look at what that decrypted file looks like. So I'm saying cat pk decrypt.text. Oh, it worked. Okay. So and of course, if I said diff plain text.text and pk decrypt.text, there's no difference between them. So we went one full cycle, right? We generated the keys. We stored the private key locally. I even encrypted it just so that nobody can see it. I send the public key out to the world. Somebody out in the world took my public key, encrypted a plain text, sent it to me. I took that encrypted file, decrypted it using my private key, and I have the information available to me, right? So now one thing you should keep in mind that the key generation doesn't happen every time, okay? Key generation happens once or very, very, infrequently. Why? Because if I keep my private key secure, there's no need to change it, right? Because I'm the only one who has it. Public key is out there anyway. So the key, you don't do a key generation every time you want to do a public key cryptography. You generate the key, you have it, and for a year, for 2 years, whatever, how long you want, you can use it. The point I'm making is that it's not per communication, per transaction. You use the key and you use it as often. So what you do frequently is encrypt, decrypt, encrypt, decrypt, right? But the key stays there, okay? All right, so this is good. So any questions so far? Easy enough, right? So, but now you have a sense of how to use OpenSSL for with RSA algorithm. Now, before I go on, and I'm going to look at the digital signature in a moment. Let me take a pause and sort of say this. Okay, so we have this RSA. No, not the RSA. We have this OpenSSL utilities available to us for symmetric, for public key, and all that. But you look at it, you say, all right, this is not exactly the friendliest command line that I expect to use on day-to-day basis, right? Notice we know what it does, but I had to explain every single option. And if you wanted to type this, notice even me, I look to make sure I'm not mistyping anything. So the idea is that, okay, OpenSSL has this API, this application programmer's interface that very clearly we can communicate to it what we want to do, how we want to do it, what are the inputs, what are the outputs, and so forth. But for day-to-day use, it's not exactly a friendly way of doing it. Okay, so and you remember when I put the slides for OpenSSL up, just briefly, there was a couple of slides. I said that it can be used in other programs, in other applications, right? So now, of course, I could show you an example, which I'm not gonna. I can show you an example that you could actually create a graphical user interface program, but as you're coding inside that program, make calls to OpenSSL functions, okay, to do things for you. Rather than making it really that pretty, I will do a simpler version of it, okay? So you notice what I did just in the beginning of the class. I copied 2 C files into my virtual machine. Okay, so I didn't want to type them. So let me actually, rather than showing it using Nano, probably because I would have a better chance of expanding the font and make it easy for you to read. Let me go to the file explorer, and that was, I think it's this one. We'll see in a second which file is which. All right, so yeah, this is the right one. Okay, so let me try to increase the font size if I can. And view. Oh. This doesn't seem to be any better than Nano. All I'm trying to do is to have a bigger font. So I'm going to just use Nano. Never mind. So I'm going to say Nano PK Inc.C. Now, important information for you right now. I don't expect you to be C programmers, okay? All I'm doing, I'm showing you an example C code, and I'll explain it, line by line in general terms, that what this program that I wrote is accomplishing, right? So you don't have to worry about, oh no, I don't know how to do C programs, and now I'm responsible. But that's not the case, right? So this is a C file that I wrote in one of the previous semesters. I wrote it during the class just to show the students that now you could embed, you could hide the details of an OpenSSL call inside a simple program, okay? So now just ignore whatever that you don't want to hear, but I'm just going to give you an analysis of this file. First of all, as far as C language is concerned, whenever within our program we use functions that are part of the standard C library, there's a whole bunch of standard functions that are already written, debugged, and part of the library of the C language. Math functions, input-output functions, string functions, so on and so forth. Whenever we use any of those library functions, which obviously you need to know what those functions are before you want to use them, you have to actually put a header file as an included file on top of your file, so that when the file is being compiled, it has a reference of knowing what is the detailed information about that library function. That's all it is, right? So you're helping the compiler link those library function calls to your program correctly. That's all it is, right? So whenever you see a bunch of hash or pound includes on top of a C file, it doesn't do any damage. It doesn't increase your code size. All it is, it's saying that I intend to use certain library functions. These are the reference header files for them, okay? And by the way, if you put a reference header file for a particular library and you don't use the library within your program, that's okay. It doesn't matter. So a lot of times I have like all of these pound includes in a block, and I copy and paste it on top of all of my programs, okay? So it doesn't matter, it's harmless, okay? Absence of it hurts if you need a library function, but the pound include for it is not there, but the reverse is not a problem. Put as many pound includes that you want, but don't call the function. So now, so notice it says pound include standard io.h. So anytime I use print or any standard input output library functions, I have to include this. Okay, so that's fine. Pound includes string.h. So obviously I'm planning to use some string-oriented library calls. You'll see them in a second. So that's why I'm including it. And then there's some other functions that I'm using that are in the standard library.h. So I put these 3 pound includes in there. Okay, so you know what that means. Any line that starts with double slash, which is basically borrowed from C++, is treated as a comment. Ignored. Compiler just ignores it. It's just for us human beings to read. And notice Nano already has built-in understanding of the syntax of C language, so it color codes those lines to make it easy for you to read. So Nano sees a line starting with // it makes it blue, meaning that it's comments. So you notice my eye immediately says, okay, those 5 lines are just comments. Okay, so let's move on to here. Every C program, not C file, because you may have multiple C files that combined together will give you one C program. Okay, let's not worry about that. But every C program must have a function called main, okay? If it doesn't, when you compile, the compiler complains and stops. It says, I don't see the function main, right? So you need at least one function main, and it always has to be all lowercase, can't be capital M or whatever. It looks for the word M-A-I-N, okay? Now, so that means what? That means that when you start running your program, your operating system, Linux, for example, calls a function called name, and whatever that's written inside the name will be executed, okay? So your operating system, which is a bigger program, is calling a, subprogram, which is main, okay? Now, your main could have some inputs coming to it or no inputs coming to it, okay? It's up to you as the programmer to decide whether it makes sense or not. So if after main I had put open and close parentheses, it means it's not taking any input, okay? Notice I put some stuff in here, and that's a standard way of getting input. So that's why you see, parentheses with some content in front of main. Also, main can return something, output something at the end to the operating system or not, okay? If it didn't return anything, I would have put the word void in there. But in this case, I put int. It means that it returns an integer. Now you say, well, an integer is 1, 2, 3, whatever. What's the point of the program returning an integer? It's a very common practice that if a program exits successfully, no problems, it returns a 0. 0 means no error. If it faces a problem of some sort, it returns a number, 1, 2, 3, 4, 5, or -1, -2, -3, depending on convention. And that number indicates an error code, So if a program exited and it says exiting error code 15, you look at the user's manual for that software product, it says, oh, error 15 means is such and such problem was faced, okay? So that's why we usually have an int over there. Okay, now, let's back up for a moment. I said the program gets some input. You say input from where? Input actually from the keyboard, right? So think of it this way. It's not a foreign concept to you. I type this, right? Remember, ls is a program actually, okay? If you don't believe me, let's actually look at the directory bin, which is one of the system directories in Linux. This is the name of the whole bunch of Linux commands that we use on a daily basis. And remember, green means it's executable. ls is a program, right? Somebody wrote it, compiled it. The executable is placed in this directory. So whenever I say ls, I'm calling this program, okay? So now, going back in here, whoops, clear. So this, I'm calling the ls program. But now notice, I put -l or whatever. -l is just a piece of text that I'm feeding to the program, right? So think of it. This -l is fed into the ls program, and the code inside the ls program says, oh, -l was given to me, so I should print the long form of the format, you see? So all of the arguments, all of the options that you put after these Linux commands are actually command line inputs that are fed to the program, and the program analyzes it inside. It says, oh, -l means I should do this. -a means I should do this, okay? So I just wanted to make it clear to you. What does the input to the program means? The arguments that you put after the program when you run it, okay? So let's go back to our program. Everybody's with me so far? Haven't lost anybody? Okay, so, input to the program. Just so that you're aware of it, so that, at least you have a sense of what this means. This is a standard format in C. So it's not the way I wrote it, it's the way anybody who writes C code does it. Whenever you want to input stuff, arguments from the command line, you have to have these two variables listed in your argument list. First one is of type integer. It's a number. And normally we call it argc, right? Arg count, count of arguments, okay? And then comma means another argument. That's of type character pointer, which means really an array of characters, a string of characters, okay? But it's an array of string of characters, which means that it could be one string, space, another string, space, another string. So how many of these? Arg-count will tell us, right? So when I type ls minus L, enter, an ls program is running, the ls program would say, okay, how many arguments were passed to me? Okay, and let me try each one of them and understand what they mean and so forth, right? Now, if I just did, this is again a silliness of the C language to be aware of. If I just wrote ls minus L, one argument, right? What do you think argc should be? I'm asking you an obvious question. One. It's not. It's two, actually. The first argument is actually the name of the program itself, just so remember it, okay? So, if I said ls minus L and I press enter inside the ls program, the first argument is ls, which is the name of the program. The next argument is minus L, right? So just be aware of it, not a big deal. So this is nice now. So I have a mechanism that I can pass on a number of arguments to my program, and my program can now act on those arguments that is passed to it. So this is a very useful feature. So now, I need some internal variables, okay? So, I need to store my internal data somewhere. So I have a character array of length 100 called command. I call it whatever I want, right? So it's a string. So you could figure I'm going to put some OpenSSL command or whatever in here. It's a placeholder to put a string in there, okay? I have another string of length 20. I call it file name. So you would figure the file that I want to process, the name of it, I'm going to store it in here. And I'm going to use a key, right? Because this is going to be a user interface for my decryption operation. So the name of the key file, private key.pem or whatever, will be stored in here. No big deal. Now, this is a very common way of making sure that the user entered the right number of arguments. Okay, they didn't forget something. So notice I say if the count of the arguments is 3, then go ahead and do stuff, which I'm going to come back and look at in a minute. Else, print some sort of an error and exit, meaning abort. Say, I didn't get the right arguments that I wanted. So, why 3? 1 is going to be the name of the program itself, right? So I need the name of the file that I want to encrypt, and I want the name of the key file. Okay, so notice as the programmer, I already, decided I need 2 arguments coming into this program. So I wrote in here that if the argument count is 3, proceed. If it's not, tell the programmer tell whoever that invokes my program, you messed up. I'm refusing to run the program, right? So notice usage, so this is my error message. Usage, the name of the executable, the name of the program, space input file, space public key file. See that? So, all right. So now, if the argument count was correct, what do I do? This function is a C function called string copy. It copies one string into another. I'm copying it from the argument list that came to me into the variable file name because I want to use this later on. Everybody sees that? I don't have to copy it, but I'm doing it so that the variable name has meaningful name in here, right? So the first argument was a file name, and I'm storing it into variable file name. And I'll take the other argument, which was the name of the key file, and I will copy it into my variable file name. Okay? So now I want to encrypt this file. And it looks silly. You say you're doing all of this work for one line, but remember, this could be a much bigger program. I'm just showing you the idea. Now notice, this is, I don't have to put this on. I'm just, again, echoing a statement out so that the user see what I'm doing, right? So printf means like echo, basically. So I'm saying encryption started. I don't have to put this on. I could very easily just go here and put // and I commented that, and it will never show up. Okay. All right. So, and then notice at the end I put printf encryption completed. Again, I don't have to put this. This is just information that I'm giving to the user. All right. So the key to this whole program is really one line. I've made it like 2 lines, but it didn't have to be this way. So what is this command? This C function, sprintf. It's like printf, echo, but S means string. It means print it to a string. Print whatever I'm giving you to a string. That's all it's doing. So what am I printing to a string? And I'm putting it in a string called command. Remember, I created a string called command. So I'm building some text that I want to put in the string called command. Okay? So let's take a look at what goes in there. OpenSSL, RSA utility, -encrypt, -in. So what should come after -in? The name of the input file, the plain text file, right? Notice these are, again, without getting into detail, this is how it works in the printf statement in C language. When I put %s, it means what follows is a string. And the C compiler says, what string? Oops, let's go back up here. Notice after the yellow stuff, I put the stuff that corresponds to percentages, right? So I say -in. What follows -in is the name of, it's a string. Which string is that? File name, which I already have put the file name in there, okay? -in key, the name of the input key file, %s again. It's another string. So notice in order it reads them, right? So what is the string name after file name? Key file name, right? So what does it do? It says OpenSSL RSA utility -in, the name of the file that I gave it, -in key, the name of the key file that I gave it, right? -out, and I'm just basically creating a file name by myself. I say use whatever string that was used for the input file name, but give it the extension encoded or encrypted, ENC. Okay. So notice I took the general OpenSSL command, okay, and I customized it with the specific file names that were fed to my program. You see that? So, all right, but I haven't done anything. I've just created a string. That's all I've done. Now the key is in the next line. This is a very, very powerful feature of the C language. Whenever you see the function system in C programs, it means whatever that you put in parentheses is actually an operating system command that you could put in there, okay? So, so if within my program, I wanted to run the program ls, I would say system ls. It's as if I typed ls, but my C program calls it, right? So I say system and that command. So what's going to happen? That OpenSSL whatever runs. You see that? So, and that's it. So now you look at it, say, okay, it was a lot of effort for just calling the OpenSSL command, but think of it, imagine it in various scenarios. One scenario would be this is much easier now on day-to-day basis for a person to use to encrypt a file rather than using the long OpenSSL string of options, right? Or number two, this could be a 10,000 line program that somewhere in the program I need to encrypt a file. It will be in there, it will encrypt the file and do other things with it as well, right? But of course, I made it a very short program just to give you the point. So hopefully everybody has a general understanding of this program, and I haven't changed it. So I'm going to exit. I'm not going to change anything, right? So it's there. It was the PK type. So I want to compile it. Now, and we discussed it with a couple of you the past 2 days, you can compile this file using the C compiler of Linux directly. Makefile makes it a little bit easier because Makefile, again, it's a script, okay? You don't have to do that. So I'm going to directly compile it. The C compiler that comes standard with Linux is GCC, the GNU C compiler. GCC, okay, PK inc.c, okay? Now I could just press enter, and if the compilation is successful, it will compile it to a file called a.out. I want it to have an actual meaningful name, right? So I'm going to call it -o, -o PK inc. Okay, that's it. Enter. Notice it didn't complain, which means that the C compilation was successful. So notice I have a green file now. That's executable now. Okay, so now let's just try to run this executable. All right, PK inc. I'm going to press enter. I'm not passing any arguments to it. So my argument count is not going to be 3. So the program is going to complain and exit. Right? You see, it prints that line that I have in my program. It says usage is whatever, and it terminates. Okay? So I said, oh, I should have done it correctly. So what was the name of my input file? Plain text. And the key file was popkey.pem, right? So I'm going to call my PK inc, but now I will add arguments to it. I'm going to say plain text.text and popkey.pem. So it's going to take these 2 strings, pass them on to the program. The program will put it into an OpenSSL command, call the OpenSSL command, and the rest is done. Okay. Notice encryption started, encryption ended. So now if I look, a new file got created called plain text.text.enc, because of the script I had written in So my whole point out of this was that, okay, it may take me 5 minutes, 10 minutes, 20 minutes, depending on how good a programmer I am, to embed this into a C program. But once I do it, now it becomes a very easy utility. Notice rather than writing all of that long string, all I did was, oops, I keep doing that, clear. I just use PK inc, input file and key file. You could make it even smarter. If you know that, I always use a particular public key file, you could even build that name hard-coded into your program, So, I mean, there's all sorts of tricks that you can use. But at least this is general enough, because sometimes I want to encrypt it for her, sometimes I want to encrypt it for her. So sometimes I will use her key file, sometimes I use her key file. So that's why I left the key file to be as part of the argument list. And of course, every time I'm encrypting a different file, so the name of the file should be different also, okay? Now, this is done command line, right? So the plain C programs run as command line programs. You picture if you're writing your program in Java or C++ or in Visual something, right? You could actually have let's say a drop-down menu, right? Drop-down menu will give you the list of all of the files in your folder. You click, you select one. You will have another drop-down menu. You will select the name of the key file. Same way, it's a more sophisticated way of passing arguments to your program. And then you will have a button that says encrypt. You click on that button, what that button will do. it will call that command, right? OpenSSL whatever, right? And now a new file is created by your program in that folder, the encrypted file, right? So that's a much, much nicer sort of user-friendly version of doing it, right? So you will open up your GUI. It would say, this is my input file. This is my key file. Click on encrypt, all right? Or this is my input file. This is my private key file. Click on decrypt, and it decrypts it, right? Et cetera, et cetera. And then you could have, encrypt, and then you have another button, send. It actually will attach it to an email and send it, right? So I'm just trying to exercise your imagination that we're looking at the building blocks of OpenSSL, but then now you could embed it into a much larger, more sophisticated application, okay? And you're not, and then you're writing your application, you're not saying, oh, let me go get my cryptography textbook and learn how to generate a public key. No, you're just using OpenSSL. That's basically a tool for you to do your job. Does that make sense? All right. So now, one last thing I want to mention to you before we go on break. Again, it has nothing to do with the project. It's sort of your practical understanding of Linux. Linux also gives you another very powerful feature, okay, called bash files. And that allows you to put a sequence of commands in a script file. And just by calling the name of that script, it would basically run those sequence of commands automatically for you, okay? Now, what I did in the C file can accomplish the same thing as well. Notice I could have a bunch of system calls one after another. Actually, in fact, let me do that to make a point for you before I go on, so that you see you could actually use this program that I gave you to do all sorts of interesting things. So let me nano this file. Actually, no, let me change the, I'm going to change the name of it once I want to save it. So I'm going to got this program, okay? I don't need any of this stuff. I don't need any of this stuff. I'm making the program much simpler, just to demonstrate to you how powerful C and Linux together are. Okay, so, and I actually don't even need those variables. Notice I'm just basically taking out all of the program effectively. Whoops. All right. Notice what survived. Okay, so I'm not going to even use a variable called command or anything. I put the command directly in double quotes, right, which is a string, okay? I'm deciding that the first command I want to run is ls-l, okay? I'm deciding the next command I'm going to run is date. I'm deciding the next command I'm going to run is ps minus AEL. You get the point. I could put 15 different commands in here, right? So now I'm going to say Control X, yes, but I want to give it a different name. I'm going to call it myscript.c. All right. So notice now I have a file called, do you see it? Yeah, myscript.c, right? So I could use the GCC to compile it. So myscript.c. And let's say the output of it would be, whoops, my S, okay? All right, so now look what I'm gonna do. See that, what it did? Of course, that's the PS command, right? So notice, when I ran it, first, it ran the ls-l, then it ran the date, then it ran the PS command, right? So I can do scripting of multiple C commands in a C file as simple as that system, and run it, right? I could give it more intelligence and put if statements in there, right? If argument 2 was such and such, run this sequence. Else, run this sequence, and so forth. So, and that's how most of these commands are written, right? So ls program, it says if argument 1 is minus L, then do such and such. Else do such and such. Else do such and such. You see that? So I can do scripts using C language, fairly easily. But I want to show you another feature also, and then we'll go on break. We're almost done. After the break, I'll do digital signature and we're done. But let me just Google this for you. So I'm going to just basically say creating bash files in Linux. Create bash file in Linux. So let's say you don't know any C programming, you don't want to learn C programming, but you would like to create automated script files, right? So this is one way of doing it. Okay, so you create a file whose extension is .bash. Okay, and what is bash? Born again shell script file, right? So .bash, B-A-C-H has to be there, right? The first line in that program, in that file, should always be this, the strange looking text. Pound, exclamation mark, /bin/bash, right? That says read the rest using that utility that reads script files, okay? Then you would put whatever you want after it. You don't need system anymore. You put the actual Linux command in there. You save the file, and then you have to add executable permission to that file using the chmod, okay? So name of the file, this should be the first line in it, and then you make it executable. So let's go through this, a non-C version of creating a script file. So let's do this. Let's go over here. I'm going to say clear. I'm going to say nano. My B for bash file, .bash, right? So that's condition number 1. The extension should be bash, okay? Now, then the first line was bin bash, right? I just want to make sure I didn't, yeah, bin bash. Whatever I put from now on is the commands I would like to put, right? So I'm going to say clear. I'm going to say echo, good morning. The time is. Then I'm going to say date. Then I'm going to say sorry. You get the picture in here. Echo, your files are. I'll do ls, right? And actually, let's do this. I'll put the CD. So go home first, then show the files in it. So you notice you could customize exactly what you want to do. Now I gave you a silly sequence of things, but it could be actually every night you want to run a bunch of programs in sequence. Updating, for example, it would be this. I'm not going to do it, but I'm going to show it to you, right? I could put in here sudo apt-get update followed by sudo apt-get upgrade, right? So I could run this script every night, and it does the latest updates for my Linux. You see that? So you put as a administrator for your server, Linux server, you will put whatever commands that you want to put in there, right? So all I have to do now, I save it, and again, any Linux commands you want. So Control X, yes. Now, I cannot run it as a bash file because it's not executable, right? So I'm going to say change mod, you know that what that means now. User, group, and others plus X, and might be that bash. Notice it became green now. If you don't believe me, let's do an ls minus L. You notice it now has, wait, it doesn't come up on. Notice the X appeared. So I took a text file and I just set its X bits to true, and now Linux treats it as an executable, okay? So what I have to do now, I have to run it. And the way to run it, you will simply send /, right? So let's come back in here, clear. And I'm gonna say, you see that? So I didn't write any C programs in here. I just created a script file, a bash file, okay? And again, bash file is not necessarily just a direct sequence. It could have if statements and so forth. You have to learn the language of the bash files. It's a scripting language. So you could make that sophisticated also, but I give you a very simple version of it. Command, 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 right? Okay. Now, you could create any bash file that you want, but there is one bash file that exists and automatically gets executed every time you open up a terminal, okay? So now let me go home. I'm gonna go ls. You say, I don't see it there. It's a hidden file, okay? So if I say ls minus a, which means show me all of the files, even the hidden files. The hidden files are start with dot. You notice there's a file called .bashrc. The name is very special. Linux knows it. And this is a script file that gets executed automatically every time you open up a new terminal, okay? So I can customize this, okay? So now that I know what the name of it is, I could say nano.bashrc, and this is, you know, what is, you know, by default over there. Now, I could put at the end whatever I want, right? So I'm very pleased with myself, right? So I would say echo, hello, handsome, right? Because I want my computer to always greet me as a handsome person, right? So I'm gonna say Control-C, Control-X, yes. So my bash RC now got updated. Let's exit. So I close my terminal. So next time I open up my terminal, let me zoom in. Notice my Linux box loves me. You know, whenever I open the terminal, it says hello, handsome. So you get the point, right? So now you could put, you know, customized commands. You want to go to a particular directory. You want to list the directory. You might even want to run a couple of programs to do certain, you know, you put them in the bash RC. Every time you log in, you open up a new terminal, all of those will automatically be created. So it's a script file, but a special script file. But you could generate your own script files as you want also, right? I'm going to delete this. I don't want this to embarrass me later on. So I'm going to say nano.bashrc. And all right. So now the only thing we have left, so that the whole point I was making during the last half an hour or so was that once you know the OpenSSL commands, you can embed them into any application that you want. and of course into a script file. So it is now 10:30. Let's take a 15-minute break, and at 10:45 we'll come and finish the last part of Project Digital Signature. And the attendance sheet is here. Everybody sign it? Okay, very good. You didn't sign it? Resume recording. All right, so now the last part of the project has to do with digital signature, and I sort of, again, in general terms, explained to you what digital signatures are. So let's get a little bit more specific, a little bit more detail, and then we're going to run this in OpenSSL. So not very easy to read, but this is the basic picture I want to tell you. Now, what if I want to send some important information to the recipient, to destination, but accomplish two different things. Number one, encrypt the file, the plain text, for privacy so that nobody else can look at it. So that's one goal. Number two, digitally sign it so that essentially the receiver is guaranteed that the message came from me and from me only, okay? That I have digitally signed it, okay? So there's really two different steps to it. One, encrypting it for privacy. Two, digitally signing it, okay? So that's why I just spent a couple of minutes creating a very quick diagram in here. So step one means whatever your plain text is, use symmetric key cryptography, you know, AES or whatever that we used yesterday to create the ciphertext, okay? And you will send the ciphertext, you know, so that protects your plain text against Oscar being able to open it, okay? So this is project 3. There's nothing new about it. Next thing is to now ensure that the message is digitally signed, okay? So now take this ciphertext, and you know the diagram I had before, I just put this ciphertext next to it. These two are the same. So what is called data in this diagram is the ciphertext in the previous diagram, okay? So our starting point in this picture is the original plaintext file that was encrypted using AES or whatever, and now it's protected against unauthorized access. Now I want to digitally sign it, okay? So first thing I do, I take that ciphertext and I feed it into a hashing function. Remember, the hashing function accomplished what? It used the mathematical algorithm that converted this binary file into a fixed size hash, okay? Now, this accomplishes two things. One of them is that, you know, what I would feed to my digital signature process is not a file of various lengths, is always a fixed length entity, okay? Under 28 bits, whatever the case might be, number one. Number two, remember I said the hash functions I just want to create a new slide. Remember, hash functions input, right? So this is one input, this is another input, this is another input, this is another input, etc., right? Hash functions have a one-to-one correspondence, meaning that this input will give you this hash. This input, whoops. This input will give you this hash. This input will give you this hash, right? So there's a one-to-one correspondence, okay? So you notice the inputs are different lengths, but the outputs are all the same length, right? Now, why is it a useful information for you to remember right now is that once I create a hash of an input, okay, if the somehow the contents of this input file would change, the hash of it will change, right? So the hash acts almost like a CRC or a checksum that says if anything in the original file changed, the hash of it will change also. So it's also a guarantee against hacking and changing of the writing the into that file, changing the content of the file. Okay. So now going back, so I take my already private cipher. Could we have no talking in the back, please? No talking, please. Feed it to the hash function. Hash function gives you a fixed length hash. Okay. Now, take the fixed length hash, which is basically compressed. Think of it, it's not compressed, but the compressed version of the file. And now encrypt it using your own private key, which you never give to anybody. Okay. And now, what you will send out is basically the data, which is this guy, right? And your signature. Okay. Now this is over the open network. All right. So now you notice why I encrypted my data. I don't want to send my data open network unprotected. Okay. That's why I encrypted it first, right? Using AES or whatever. Okay. But this data could have come from anybody. Okay. I want to make sure that the recipient has a guarantee that it came from me. Okay. So I do send the data using AES encryption, but now also attach to it the signature that just got created. Okay. So it travels over the internet. Okay. Now the receiver receives it. Okay. Now for a moment, I'll change it in a minute. For a moment, imagine that who received it is Oscar, the bad guy. He's not supposed to be the recipient, right? The Oscar can take the signature, okay, and decrypt it using this guy's public key. Is it possible or no? I'm just talking about this part. Can Oscar decrypt the signature using the signer's public key? Why not? No, I'm not talking about this. I'm just talking about the signature, right? My public key is available to everybody, right? So Oscar should not have a problem decrypting the signature, right? But once decrypts it, what is it going to get? It's going to get a hash of the signature, right? And even if magically he managed to unhash it, what is it going to get? A ciphertext that was encrypted using AES or whatever, right? So yes, Oscar can decrypt the signature, but it's not going to take him far. He's not going to really get access to the actual payload, the actual data, right? So the reason I brought this up is that that's why I used AES or something to encrypt my original data. Anybody can decrypt the signature because the signature is being decrypted using my public key. My public key is available to everybody, okay? So I take my original plain text, I encrypt it using AES, I feed it to the hashing algorithm, I get the hash of it. The hash of it will be encrypted using my private key, and that would generate my digital signature. I will send the digital signature and the ciphertext over the open internet, okay? Yes, Oscar can receive it. Oscar can decrypt the signature, but that's not going to help him much, right? But now imagine if Bob receives it. So Bob is going to do what? It's going to take my signature, use my public key, okay, and decrypt this and come and take the output, which is a hash, right? Which is a hash, and hold on to it. Then take my data, okay, feed it to the hash function also, okay, and come up with the hash and say, is this hash equal to this hash, right? If they're both equal, that means that the file that was received was signed by the signer, created by the signer. Why? Because the signer is the only one that he has his own private key, okay? So it is authentic, okay? It came from the right person and it wasn't changed, because if it was changed, the hash would have been different. This hash and this hash would have been different, okay? So now what Bob has accomplished is the fact that I received some data and I know it came from Alice, okay? But now Bob needs the key to whatever this AES was to decrypt the file, okay? And I'm not worrying about it. Let's say Bob somehow got the key, okay? But the whole point I want to make in this picture, which has become awfully crowded, is that just don't put your raw plain text in here, okay? This picture takes care of the digital signature, but remember, it's not protecting it for privacy. Everybody in the world has my public key, okay? So everybody can decrypt this information, right? So the actual payload itself should be previously encrypted using some symmetric key cryptography. Why am I so symmetric? Because probably this file is large and it's too large to be encrypted using public key. That's why, all right? So imagine if this was a 2 megabyte file, encrypted using AES, incorporated into digital signature and so forth. But you get the picture what the idea is, okay? Now that you know what the process is in principle, again, we don't want to keep doing this every time we want to digitally sign a document. So we will use OpenSSL to help us. Okay, so going back to let me zoom in one more time. Going back to our project, okay? So, let me go to project 3, because I think I had a, no, change directory, BDB, change directory, project 3, because I think yesterday, project 4, sorry, change directory, project 4. Okay, so remember my ciphertext that encoded was the AES encoded ciphertext, okay? So I'm gonna just save time and just use this file, okay? So this is my protected plain text. So I'm going to basically take this file, copy, CP is copy ciphertext that encoded to go up one level, go to project 5, okay, and call it project 5, okay? So I'm going to go up one level and go down to project 5. All I did, I just moved that encrypted file in here, okay? So that's the, where is it? This is my data, okay? So now I want to digitally sign this file, okay? So let's clear this mess here. All right, so I'm going to do this. I'm going to say, OpenSSL RSA utility. So digital signature is part of RSA utilities. What do I want to do? I want to sign. I want to digitally sign a file. What file? The file that I want to sign, right? So I call it what? Cipher something, right? Cipher text unencoded, right? Minus out. So what would be the output of the signature process? Okay, let's call it signature.tar. Okay, so I'll come back to it in a second. I just want to put this up. So I'm doing the signing, right? So I need the original data, which was that ciphertext encoded, right? What is the other thing that I need to feed to the signature process? The private key. Don't forget that, all right? So let's go back in here. So I do need my private key, right? So dash in key means that now I'm giving you my private key. And the private key, I think I called it prikey.pem, right? Done. All right. So let's take a look. The file's created. So the red file, signature.tar, is the signed, digitally signed version. So it has that hash built in, encrypted using my private key, and it's now ready to be sent out. So I take this red file, I'll email it, I'll send it to destination with any means that I like. The recipient receives it. Okay. Now, the recipient has my public key. Okay. So now pretend I'm the receiver, right? So suddenly now I'm changing roles. I'm the receiver that received this red file. Okay. So I want to verify that this file is correct. Okay. So I would say OpenSSL RSA util. Okay. Last time, notice the sender did dash sign. This time, the receiver does dash verify. Okay. What is the file we're trying to verify? Signature.tar, right? And minus out. Yeah. Digest sign dot text. All right, so we say verify this file. This is the name of the output file. Okay. What other piece of information do we need to feed this? Public key, absolutely, right? So dash in key, and now pretend that that was my key, right? So pubkey.pem, and the only other option we need to give it is that the key that they're feeding you is the public key. Okay. And now a new file got created called digest sign, right? Digest sign that text. Let's just look at it. It's a binary file, right? What should this file be? This file should be equal to the original data, that ciphertext encode. Not 100% sure, but I think that's what it should be, right? Let's do a diff between this file and ciphertext encode. Good, yeah, all right. So now what have I accomplished? I have now recovered, I've recovered this file that has guarantee that this came from the proper source and it wasn't modified. but still notice it's still encrypted. So I have to use AES decryption with the proper password, with the proper key to decrypt it, which I skipped right now, right? But everybody sees what's going on, right? That's why I encrypted it. Otherwise, anybody could use my public key to, unsign it to verify the signature, all right? So that's basically the process. Now, you could do this all the time now, so a lot of times right now, nowadays, I'm sure it's done in Canada also, but a lot of times if like students have to file some application with the US government online, okay, some application for a loan or for whatever, in the older days, of course, they signed the application and they sent it in the post, in the mail. Nowadays, basically, it's a PDF file that you create and digitally sign it, and then you click on submit. Okay. So what does that mean? That means that the U.S. government that receives your PDF file knows that it definitely came from you because it was signed with your own private key. Okay. So and that basically becomes a legal version of electronic signatures, right? Or an electronic version of legal signatures, right? So as opposed to having it legally written on paper, you now have a legal version of your electronic signature. Okay, so that's that. Now, and that's the end of your project. So once you do this, digital signature, that would be the end of your submission. But when you look at your Project 5 help, and I urge you to read it even though you're not submitting anything, after the digital signature section, it has a tutorial on public key infrastructure, PKI. I just read you a couple of lines of it. I already described it briefly in the past so that you know what this is all about, okay? It says, one of major breakthroughs of public key cryptography is to solve the problem of, oh no, that's not what he wants. No, that's not what he wants. Public key infrastructure, that's public infra. The public key infrastructure is a centralized solution to the problem of trust, okay? Remember what I just mentioned. I digitally signed it, but how do you know I actually am Alice? Okay, it came from a person who claims to be Alice, but how do you know am I really Alice? Or maybe as somebody else that I'm pretending to be Alice, right? So trust. The idea is to have a trusted entity, an organization, a corporation, that will do the job of certifying that the given public key belongs to really a given person. Okay, so yeah, I gave you my public key and you verified my signature and you realize, yeah, no, it came from me. Okay, great, it was me, but who am I? I could be anybody, right? The person must be identified by his name or her name and address and other useful information that may allow to know who this person is. Once this work is done, the PKI, the public key infrastructure, emits a public certificate for this person. The certificate contains, amongst other things, one, all the information needed to identify this person, name, birth date, etc., etc. If it's a corporation, maybe their government tax ID or whatever. The public key of this person, the date of creation of the certificate, and the date of revocation of the certificate. So just having a certificate is not good enough. If your certificate expired 3 years ago, it's useless. It needs to be valid today. So that's why you have to keep renewing a certificate. The digital signature of all this previous information emitted by PKI, and so on and so forth. So OpenSSL actually allows you to create your own certificates. You could actually get your certificate, set up your website, set up your e-commerce business, and do whatever you want to do, right? So it's not that, such a complicated process. OpenSSL actually allows you to actually register yourself with, to have a certificate. I could have assigned it as part of the project, but I figured that, that's enough for Project 5 scope, but I wanted to make you aware of what comes after that. So hopefully you've gotten a good sense of the power of OpenSSL. generates prime numbers for you, generates random numbers for you, does all of the symmetric key cryptography, does all of the public key cryptography, does certification, digital signatures, and a bunch of other things, right? So very powerful tool. And now you notice that all of that power can be embedded into your program, your application, your app that's running on your smartphone, as well as creating a script in Linux and whatnot. Okay, so all of these things can come together. So with that, I've covered all of the hands-on components of this course. So hopefully by the end of the semester, you feel comfortable enough. It's okay, yeah, I'm not an expert in Linux, but I know my way around. And if I get stuck somewhere, I know now how to poke around, do a little bit of Google search, and figure out what to do. I haven't talked about a lot of configuration files and the other things, but this is a good start. Now you're not worried that, okay, I've never touched Linux. You're comfortable with that. With the textbook material, hopefully you find it to be easy enough. So remember, tomorrow when we meet at 3 o'clock, I'll give you the exams. It's on chapters 1, 2, and 4, multiple choice questions that I mentioned to you, and a few questions on project 1 only, okay? And once you finish the exam, you hand it to me and you leave. You know, either you go to your communication class or you're done. And then from next week on, obviously, we go back into the remote mode of the course, okay? Any questions or comments at all about what we've done? Everybody's comfortable? All right. This time, I think I recorded it, so I'm going to hopefully upload it and put the link for you in Blackboard. So with that, I think we're done, you know, actually 45 minutes early. So thanks for coming 4 days in a row. You know, I know it changes your schedule with respect to all your other courses. I'll see you tomorrow for the last time for the exam, and hopefully we see each other later. All right. Bye. Class is over.